Thanks, Matt. It's my pleasure today to introduce James Wood, Ph.D., PE, an indoor environments consultant residing in Charlottesville, Virginia, and the former executive director of the Building Diagnostics Research Institute. Previously, Jim was the William E. Jameson Professor of Building Construction at Virginia Polytech Institute and State University, and he served as Senior Engineering Manager and Senior Staff Scientist at Honeywell. Jim was also Professor of Mechanical Engineering and Architecture at Ohio State University and has over 49 years of experience in energy and environmental analyses, and has been responsible for more than 30 research projects and 250 investigations related to indoor environmental quality, energy utilization, and human responses in buildings of all types. Jim has served as a consultant or advisor to many private and public agencies, including design engineering and architectural firms, building owners, insurance companies, law firms, utility companies, and state and federal agencies. I'm looking forward to today's presentation, and with that, Jim, I'd like to turn it over to you.
I want to thank Mark for the invitation to make this presentation. I've been looking forward to getting some feedback from everybody that's on the line. The title that we've chosen is Specifying Building Performance. Most of the time, specifications are written in a prescriptive language, which allows precise definition of expectations like dimensions, physical properties, and things like that. And the corresponding methods of measurement and evaluation. But performance specifications present a different challenge and some opportunities. The primary challenge in defining the aspects of performance is defining the aspect of performance that are measurable and that meet the functional requirements of the building or system. The primary opportunity is that the finished product can result in an interaction of all of its parts that can be evaluated as a complete system in terms of functional requirements. What I'd like to do today is address 6 questions. First is, what is the fundamental purpose of buildings? Then we'll go to, what is building performance? Then we'll go to the question, is there a critical set of measurable parameters? If so, then the next question is, what values of the parameters should be specified to assure delivery and operations of high-performance buildings?
Hi, Jim. It's Mark. Have you advanced your slides?
I have not yet.
Okay. I thought that those 6 points. Sorry for interrupting.
Yes, sure, Mark. Thank you. The 5th one is, who's accountable for assuring building performance? And then the 6th is, where do we go from here? So starting, what's the fundamental purpose of buildings? I like to look at it as providing safe, secure, and healthy conditions, first of all, and then secondly, facilitating the well-being and productivity of the occupants, owners, and managers. For purposes of what we'll talk about today, I'd like to consider that we're addressing 6 functional categories: residential, not necessarily single family, but residential, large residential, educational, healthcare, office and mercantile, public assembly and worship, and industrial. Along with the purpose, and we need to look at the fundamental objectives of environmental control to achieve that purpose. And I would propose that there are 2. One is to prevent adverse health and safety effects during both normal and extraordinary conditions in and around buildings. And we'll delve into that in just a few minutes. The second is to provide for desired conditions in terms of human response, occupant performance, and productivity. To achieve those objectives, then we need to consider simultaneous control of 4 exposure parameters: thermal, air quality, lighting, and acoustics. To meet those objectives, let me propose that we base this on two fundamental principles. One is called the Maslow hierarchy of needs. And there's 5 levels of needs, and they're in order. So the baseline is physiological needs. Once we satisfy that, we look at safety and security. Then we look at the higher order needs of belonging, esteem, and self-actualization. Most of us are used to dealing with the first 2, but not necessarily the last 3. And so we'll be spending some time on that. The second fundamental principle is an old-timer. It's the definition of health that's in the World Health Organization Constitution, which is a state of complete physical, social, mental, and social well-being, and not merely the absence of disease or infirmity. The importance here is there's 2 aspects to that. There's the public health aspect, which is the complete set of physical, mental, and social well-being. The second is the clinical definition, which is the absence of disease or infirmity. So these 2 principles work together quite well. The question I would pose here is, how do performance specifications relate to these 2 principles? And when we get into the discussion section, maybe we can talk about that for a minute. Now, related to that is the 6 principles of sustainable design. And I've taken this out of the whole building design guide from the National Institute of Building Sciences. It comes out of the federal government mostly, but if you look at those 6 principles, they're almost upside down from the Maslow hierarchy. And this presents an interesting issue because in Maslow we start with the health and safety issues, and then we work up to the higher order issues, looking at the energy, the environmental, and sustainability issues as consequences of dealing with the other factors. These sustainable design principles kind of turn this upside down and start working with the optimization of the site and the energy use, and then conservation of water. And finally we get down to then looking at enhancing the indoor environmental quality and dealing with the operations and maintenance procedures. As a professor, I used to tell the students, if you want to minimize energy in the building, don't build it. But if you are building a building, you're doing that because you're going to occupy the building, and once that building is occupied, you've made a lifetime commitment to be able to protect the health and safety and functionality of the people in the building. So we need to kind of turn things around and understand what the priorities are as we begin to set our performance criteria. So I think with that, Mark, I'd like to stop and see if anybody's got any questions on our first set of concepts here.
Thanks, Jim. One question that I have is that a lot of sustainable design in the country is driven by the USGBC these days, with LEED and their 30,000 people who go to their trade show and the 11,000 buildings that have been certified, and they match up pretty well with what you have on the screen in the 6 categories: site, energy, water. Do you think we're missing the boat? Should we?
Yes.
Okay.
If you go back to the Maslow and you look at health issues, they're really not discussed very much in the LEED process at all. Safety and security is to a little extent, but not much. And we see this strong focus on materials, on energy, and on sustainability, but not in terms of the occupants themselves.
Well, it's the same way with the building codes. They're often there to protect the buildings and not the people. Matt, has anybody put in any questions, or should we continue on? I'm certainly in agreement, Jim, with the fundamental principles. One makes sense, and then, but perhaps the issue with LEED and other groups is they don't see safety and security as their territory, and so the same way the someone whose priority is to build tall buildings, they measure by how tall is the building. So
Yeah.
but I guess if sustainable design when it comes to people can be quantified, then that would be terrific.
Well, I hope by the end of the session here we can talk about that and say that really is what sustainability is all about.
Okay, I don't see any questions that have come in, so if we can move on, that would be great.
The second question then is, what is building performance? And I'd like to start this discussion with the definition that I was asked to develop a few years ago for the International Society of Indoor Air Quality. It's now been published, but it's based on control theory. In assuming that the building is a total system, we can define building performance then as a set of measured responses of a building as a system to anticipated and actual forcing functions. And there are two big terms in there. One's measured responses. We need some assurance that the responses are valid and reliable parameters. And you'll see a list there. We'll talk about that a little bit later, but I like to ordered list of first thing we need to look at is human response. That's caused by exposure. Exposure is caused by system performance, and system performance has an impact in terms of economic performance. So the forcing functions are known physical and social forces that are likely to perturb the building system to which the response functions occur. Some of these are normal, the climatic, the design temperature and humidity, outdoor weather conditions. Others are natural phenomena, earthquakes, wind problems, flood problems. And we'll get into this in a little while longer, but then there's other social forces that actually will act on the building that we need to deal with. So psychosocial forces can have quite an influence on what we're doing in buildings. Taking that to another step then, there's a definition of high performance building in the ESA 2007. That's the Energy Independence and Security Act of 2007. And in this definition, the term high performance building means one that integrates and optimizes on a life cycle basis all major high performance attributes. And these include 11 different attributes that I'm showing here. The first two, energy and energy conservation, environment, we do a lot with. Safety, security, durability, and accessibility we do less with. The cost benefit, we tend to do a life cycle cost analysis, but really not cost benefit. We don't seem to spend a lot of time on productivity. We do think about sustainability. Functionality is something that we need to worry about, and operational considerations is something that we hardly deal with at all. One thing I noticed in this definition is the attribute of health is not included, and so I would propose that we really have 12 attributes that we ought to be focusing on. Also in the ESA 2007, there's a term that some of you may have run across, some may not have heard about it yet, called zero net energy. Others call it net zero energy, and either way, I think it's a disaster that it's impossible to meet this thermodynamically. But it's policy, and so we need to deal with it. The term zero net energy in commercial buildings means a commercial building that's designed, constructed, and operated to meet these four conditions. First is to require a greatly reduced quantity of energy to operate. My first question is, how do you measure greatly? once you get to the point that you've reduced the energy consumption in the building, and that presumes that safety and occupant exposure is taken care of, but it doesn't necessarily say so. B says that the balance of the energy, what's left, the residual amount of energy that you've got to supply, must come from sources of energy that do not produce greenhouse gases. This is really important because sources such as biofuels don't pertain, because a biofuel is going to be a form of combustion. It's going to produce CO2 and other greenhouse gases, and so it's precluded. So about the only thing we can look at is photovoltaic, solar, thermal, wind, items like that. Item C, the product then of using the renewable resources has to result in no net emissions of greenhouse gases. And then the fourth, which is a huge loophole and gap, is it must be economically viable. And the viability of the economics in which you're trying to do this is not defined. So again, from a policy standpoint, you can do almost anything you want. I've seen examples now where the amount of energy reduction was almost insignificant compared to the average amount of energy used in a building, say in the energy utilization index. It's somewhere around 50 or 60,000 BTUs per square foot per year. And then they go ahead and put huge photovoltaic banks up to be able to deal with a small percentage of the energy used, mostly electrical. And when you look at what's being done from the resource standpoint and then apply item D to that economic viability, it really becomes a problem that we have to deal with. So as we move forward with zero net energy, I think we have to do that with great caution. What I would propose is that we look at building energy efficiency. And in the middle, the upper middle of that diagram, you'll see indoor exposures, which I like to think of as the driving force of what we're doing. So in order to develop a building energy efficiency, the first thing we have to look at is the forcing functions, and there's two. There's the envelope load and the internal load. That will give us a passive amount of energy passive amount of load over time. And to do energy rather than power, we've got to look at an integration over time. So we look at this passive integration of the balance between the internal loads and thermal loads in terms of the exposure. And that will tell us time out of bounds, time out of criteria. That tells us then the type of system and the energy required in order to come into exposure control, into acceptable exposure control. The amount of energy consumed to achieve that energy required then also causes energy waste. So if we look at building energy efficiency as the ratio of the energy required to achieve the exposures divided by the energy consumption, what you see is that the energy consumption is the sum of energy required and energy waste. The work that we've done, what I've been involved in, I guess, for the last 30 years, is looking at some of these numbers, and what we typically find is a building energy efficiency of about 50%, which basically tells us that the amount of energy we're wasting to get to the required energy for our exposure is almost equal to the energy required. The waste is almost equal to the energy required, which gives us an awful lot of room for improvement. So I would propose here that one of the focuses we ought to be working on is minimizing our energy waste, measuring it and minimizing the energy waste in order to get to the energy required necessary for our exposures. And again, Mark, I'll stop there and see if that generated any questions.
Well, Jim, when you say energy waste, I've heard statistics that 30% of the heat goes out through the exterior wall, hence the changes in the code to require air barriers or to include insulation outboard of metal studs. Is that the waste you're talking of, or is that a big or small component?
That's part of the envelope load. So what they're doing with those changes would be to reduce the envelope load. The waste is going to be the relationship between the system that you've got to achieve your exposure, to come into balance between the passive system that's going to take you out of balance some part of the year, and what's going to be required to bring you in. In other words, lighting systems, cooling systems, heating systems are going to be needed some part of the year in some buildings. Now, if we trace the waste trail from the energy required back to the energy consumption, we find that we've got power losses, we've got duct leakages, we've got lighting losses, we've got all kinds of losses that we can deal with. And just maintenance of the system is going to the fan power or the combustion efficiency. All of those factors seem to add up to give us some kind of a number, like that waste component is about 50%, but it's really different than the load.
Okay, and water is generally outside this discussion. That's a separate discussion.
It is at this point. We could do a parallel model for water efficiency that, to be honest with you, I haven't focused on it as much.
Is energy waste from like geothermal less of an energy waste if it came from a power plant 50 miles away? Is waste quantifiable?
I believe it is. We've got to think about that, but I believe it is. And what we can look at, again, from the energy consumption standpoint, we could get a pretty good handle on our energy consumption. The biggest issue I have is actually measuring the energy required, because you've got to draw your boundary around the exposed occupants. And this becomes a problem. The energy consumption we could do with a meter.
Okay. In Massachusetts, there have been a number of zero net energy buildings in it, and I guess I'm in agreement with your comment that zero net energy does not actually mean zero. It just means as best you can. Is that
right.
That's actually the definition. Because I've seen, we have a bus station that is loaded with solar panels where the doors are open quite a lot of the time because people are coming and going to the buses. And the buses, of course, are using whatever fuel. So I suppose it's good to have a regional transportation center and good not to have people in individual cars. But, so you're saying, could you expand your envelope to the building and how the building is used, or is it really just the building inside the doors?
No, well, as long as you're dealing with the exposure and the physiology of the occupants, you could expand it. As long as you're meeting the needs of the occupants. So if you're meeting the safety and the health aspects of the people on the property, you could certainly do that.
Okay, and Doug asks whether we're talking about lifetime energy consumption, including fabrication, operation, and disposal?
You can do that. This does not preclude it. The two issues that you have to look at, one is the time frame that you do the analysis, the energy analysis. Energy is power times time. And so when we talk about energy, we have to talk about a duration. The other is what the components would be. If I look at energy requirement and I talk about embodied energy required rather than site energy required, it would just be, I'd have to figure out a way to measure that. But yes, it could be done.
Okay. Thank you. I think we don't have any other pending questions right now.
There's this is Matt. There was just another question from Doug from a few slides ago. I was wondering if, Jim, you could just kind of better define or describe, you had mentioned the idea of control theory, and Doug was wondering if you could explain that in a little bit more detail.
Sure. As far as the definition of building performance is concerned, the concept of control is, let me put it this way, the old concept of control is that we have a closed loop system, a feedback system. And so we have a forcing function, we have a response function, and then we have some kind of a manipulated variable that relates our forcing function to the response function. That's where the control theory would come in. For a simple example would be a thermostat. That we've got a thermostat in the space. It senses that the room is too cold. It turns the switch on and it engages the heater. When it gets warm enough in the space, the switch goes off and the heater goes off. That would be the feedback loop. And the measured response in this case would be temperature. But we can do that with any of the exposure parameters that we're dealing with.
Thank you.
Okay, are we ready to move on?
Yes, thank you.
Okay, so the next question is, there a critical set of measurable parameters? And I propose to you that we can look at this critical set as an epidemiologic model on top of an economic model. So in series, we've got human response, and then we've got exposure that is the stimulus for the human response. The exposure is controlled by systems. The system responds to sources or loads, and that whole chain rests on a bed of economics. So we have to look at our systems in terms of first cost, operating costs, energy costs, and productivity or outcome of the whole chain. So what we're trying to do in this particular case is an optimization model in terms of looking at the performance of that whole system. We want to get acceptable human responses. In order to do that, primarily we're going to have to control the exposures, and the exposures then are based on our ability to have systems that would meet those needs, and then we have to recognize the type of loads and come up with the type of engineering solution to that would meet our economics. In the last few years, there's a new control paradigm that we also need to look at, and I want to spend a few minutes talking about it. This is resilience. So the first point is to assure energy efficient and cost-effective performance under normal conditions, which with, say, a 100-year life of a building, 90 years of that life are probably going to be under normal conditions. But we may have a few quakes, and we may have a few floods, we may have a few extraordinary conditions that we've got to deal with in that 100-year period. So we need to think about that in preparedness. And then the third part is, what do you do with the people during the event? during 9/11, we were getting calls immediately. What do we do in a tall building? Or with the anthrax scare, I guess it's more with the anthrax scare. What do we do if we think there's a anthrax scare in the building? Do we have to shut the whole building down? And if you're in a 60-story building, the last thing you want to do is shut it down. But you do need to know how to respond safely under those extraordinary conditions. So one way to look at that is that we've got the concept of residual risks here. We've got threat, vulnerability, and the risk of any kind of an extraordinary condition. So during normal conditions, we're going to be worried about our health and comfort and performance. During extraordinary conditions, if we take the normal conditions and superimpose on that natural forcing functions such as wind, flood, and quake, you're going to go a long way towards resiliency of the building. Beyond that, we've got accidental issues, flood, fire, spills, and things that need to be taken care of. Then we get into the intentional threat or vulnerability in terms of either criminal conditions, which we have to deal with in terms of arson or sabotage or vandalism. And again, these are all have to be considered from the specification standpoint. And finally, terrorism in blast, CBR, infrastructure, and electronic. So what I would propose is that we look at the building stepwise, and you take the extraordinary conditions that are most probable in occurrence and deal with that, and then look at what your residual risk after that is. And from that, we can come up then with a set of criteria that we can work from. Okay. See if there's any questions on that aspect. It's a mouthful, but
well, it's residual
total building performance.
Residual, get my tongue untwisted. Residual risk. Residual risk. Does that mean the event could happen again, or it means that the occupants are safe at the end of the event?
Yeah, well, that's a good question. Residual, as I intended meaning here, is once you look at the normal conditions and the risks toward exposure or hazards that occur because of the forcing functions, if you've only dealt with the normal conditions, your residual risks are high.
Okay.
If you deal with the natural hazards, you're going to reduce the risk somewhat, but you're still going to have some residual risk. So you diminish the residual risk as you attack more of these forcing functions.
Thank you. Okay. And Mary comments that residual risks could include drought, power shortages and outages, perhaps sea level rise?
Yep, absolutely. So in writing performance criteria, these forcing functions need to be taken into consideration. And the question then is, what response function are you going to specify?
Okay, and I guess if there's an economic component, it depends on how long you'll own the building. If you've got a waterfront restaurant right on the beach and you're only looking about this year or worried about this year, that's different than if you were concerned about sea level rise.
Oh yeah, absolutely. Yeah, the big difference here is defining hazard versus risk. The hazard is likely to occur, but if it occurs and the consequence of its occurrence is low, then the risk may be low, or vice versa. It may be a very minor hazard, but the risk could be extreme.
There's also been an emphasis about first responders to a building, usually the police or ambulances or fire. So that would seem to be residual risk in a very short time frame. In other words, is something going to explode again because there are chemicals in the building, or is that too short a time frame to look at?
Right, and that really addresses the preparedness and the response down at the bottom of that slide.
Okay.
What we want to do from a design standpoint is do what we can to enhance preparedness. But the other thing we need to do is understand what has to happen during the response mode.
Okay. I don't see more questions at the moment.
Okay. Well, let's go on then to the next question, and that's what values of the critical parameters should be specified to assure delivery and operations of high-performance buildings. The way I'd like to propose that this be approached is the first thing you have to do is understand the objectives of why you're setting the criteria. And that's going to be a diagnostic effort in terms of either a virtual building or your actual building. Now, I'll introduce this contingency matrix in just a minute. But there's two sets of criteria that we need to talk about. One is mandatory and the other is flexible criteria. In the mandatory criteria, we have two terms. One would be the human response, the other is exposure. And once you've set your criteria for the mandatory issues, if you're not in compliance with those criteria, you need to change the system to come into compliance. On the other hand, the flexible criteria in terms of system performance or economic performance, you have an option. You can either change the system to come into compliance, or you can change the criteria. So the mandatory is really on the health and safety issues. The flexible criteria would be on order Maslow issues, and this is where the whole deal of sustainability, energy use and everything else comes into play. If it were mandatory, we would have to come into compliance with energy consumption, but we don't do that. We have a socially acceptable amount of energy that we use in buildings, and we're making some headway, but basically if you look at the CBEX data, it's been flat for the last 35 years in looking at all of the buildings. So we need to look at what do we mean by mandatory, what do we mean by flexible criteria, and be honest about whether or not we can change these things and how to change it. To do that, then, looking at a little flow chart, if we start out with the understanding that we're going to deal with a building client, the first question is, why are we dealing with the client? Is this a new building design? Have you been brought in because you've got some problems in the building, or what? If it's a problem building, it's pretty straightforward. You set stringent criteria, you diagnose the specific areas where the criteria are, and you make some recommendations for interventions. On the other hand, for design, if there's not a problem building, then the next question is, do you want to enhance the preparedness of the building? If you don't need to enhance the preparedness, you can use a little more lenient criteria. You're going to diagnose all the areas in the building and then see if your design does what you want it to do. If you've got enhanced preparedness as a requirement, then you're going to have to shift the criteria into a more stringent criteria and diagnose the vulnerable areas. So the question here then is, in order to set the bounds of the criteria, we need to look at what we call a contingency matrix. And in this contingency matrix, in design, what we'd like to be able to have is a healthy building and a high probability of achieving a true negative response. If we're in a problem building, what we'd like to have is getting a measurement of a positive occurrence, and and maximizing a true positive event. Now, in doing this, we get two kinds of errors. We get false positive errors and false negative errors. And we can't minimize both. We can choose to minimize either the false positive or the false negative, and the other is going to float. So what we have to look at then is what's the consequence of the type of error that we're going to make. As we become more stringent in our criteria, less variance in the criteria that we're willing to accept, the movement is going to be towards minimizing the false negative, not missing an event that occurs, but thinking that you've measured something that didn't happen. So a false fire alarm is a good example of a false positive alarm. As long as there's no harm done, you know, the fire protection people will tell you, well, it wasn't intentional, it was an accident, but you've got your system tuned up. There's no harm done. On the other hand, if you make the criteria too rigid, we're going to have too many false positives, and people are going to pay attention to it. They're going to relax, and then we're going to wind up with a false negative alarm. So setting the criteria based on these false positives and false negatives, it's very important to understand how you're going to minimize this. We can get into accuracy calculations and everything else, but I think that may be more than we want to talk about today. So what I'd like to do now is just go through a sample set of evaluation criteria, give you a little bit of a flavor for what we're talking about. In terms of human response, if you look at the evaluation criteria, ASHRAE standard 55 or 62 or the IES visual comfort probability or your noise criteria, they're all based on trying to achieve an acceptability response of about 80%. So if we don't get an 80% response, then we would be in what I classify as a P3. You're not in compliance with the evaluation with the environmental effective criteria. It's in the little green box. Worse than that, if you go down and you find that you've got more than 20% of the occupants in the building that are complaining about 2 symptoms or more that are alleviated when they leave the building, then you know you've got something associated with the sick building syndrome problem. And then even in a worse condition, if you've got more than one person that's being evaluated as clinically evaluated as having a problem, then that may be a building-related illness issue. So there's a continuity, and in design, what we're trying to achieve is that upper level, and not getting down into the lower levels. But if the criteria are not set with enough rigor, the likelihood of degrading into those other categories is pretty high, and that occurs over time. In order to achieve the human response criteria, I want to look at a couple of boxes of exposure criteria. This first one is in terms of thermal exposure. So we can look at operative temperature, we can look at thermal gradient, floor to ceiling or outdoor exterior position to interior position, or we can look at relative humidity in the range of 30 to 60%. So each of those are going to give us some information that we can decide whether or not the probability exists that we're going to have acceptable human response. Another set is lighting and noise, and I want to just take a minute to talk about this for a minute. The lighting criteria, I've got an opportunity right now. I'm working with the National Institute of Building Sciences on looking at health and safety guidance for the visual environment, with a focus on people that have visual impairments. One of the issues that comes up is the conflict between the energy issues and the lighting issues. And what we're finding is the push on energy right now is to reduce lighting power density, and that's been translated into reducing illuminance values. What we're finding with the low vision population is that we need to more than likely increase the illuminance considerably over what's being proposed in the IES handbook and interpreted by ASHRAE. So we're looking at moving toward an evaluation criteria in terms of luminance rather than illuminance. And luminance actually gives us a chance then to look at contrast ratio and daylight glare index. So one of the problems that we're finding with the low vision population is almost universally glare is a problem. And what we're finding now is daylight is a big push again from the new design on envelopes to maximize daylighting. Well, when you maximize daylighting and you don't take care of glare, we've got a problem with the occupants. The other issue is noise criteria. And we also have to meet simultaneously with the thermal and the air quality. We need to meet the noise levels in the spaces. Okay, to do that, we need to look at system performance. And there's two criteria that I'd like to talk about. One is the capacity load ratio. In deciding how large a system do we have to have for lighting or for air quality or for thermal, we look at the capacity. We look at the design load and make sure that we've got sufficient capacity to meet the load at and condition. However, that design condition is likely to only occur maybe 5 to 10% of the year. So the other 90% of the time we're going to be operating at part load control. And this puts a huge burden on system controllability. So I would propose that we use the same capacity to load ratio, matching the load to the capacity with control under all part load conditions. By doing that, we've got an opportunity to reduce waste tremendously. So the last example I wanted to show here then is examples of energy and economic criteria. The ASHRAE Standard 90 does not give you an energy utilization intensity or an energy use number. The AIA has given a number since 1974, and it's been constant basically since then at 55,000 BTUs per square foot per year. So as an example, if we look at the whole database that's out there and Energy Star and everything else, 55 is a pretty good number. So 55 plus or minus 10,000 BTUs per square foot per year is an example energy consumption rate. I would propose that on top of that, we put a building energy efficiency term on it of better than 70%, which allows us to focus on reducing our waste by a significant amount. Now, in economics, I've posted 3 numbers here. Some examples of annual cost of housekeeping, maintenance, and churn services, which should be temporary help when people leave and they have to be out of work, out of the employee service line for a while. Extra people have got to be brought in. Interesting here is if you look at the cost of housekeeping plus maintenance plus churn, we're more than double the cost of the annual cost of energy. So energy in itself, from a cost standpoint, is really not a big driver. We push on it from a resource standpoint, but when you look at it from a cost standpoint, one way I've looked at it in the past is the cost of salaries, middle manager salaries, is about $400 per square foot per year. And the cost of energy is about $3 or $4 per square foot per year. So it's about a 100-to-1 ratio. And so I have to ask the question then, from an owner's perspective or the employer's perspective, how much of my time, how much of my employee's time am I willing to waste or to put at risk to save 25% energy? It turns out in real numbers, it's about 1 day a year, or about 1 hour a day savings that compromises or that equalizes the energy savings. So if you can put up with an hour a day loss, or you can put up with a loss of a week a year of your employer because you've caused that in the environment by reducing energy consumption, then that's a risk that you take. Okay, that's a whole bunch of stuff. We'll stop there for just a minute and see if there's any questions.
Jim, there was one question about building information modeling in BIB. I know that Building Smart Alliance and NIBS have big initiatives in these ways. Are you seeing where people are using modeling to, as Doug asks, are the models sufficiently advanced to model the consequences of risk scenarios so that the specs can include contingencies for these situations? Or how should they be addressed?
Yeah, not yet. The BIM models that I'm familiar with basically front-load energy models. And so we're using the same energy model that we've always used.
Okay.
And so we don't get feedback information. What we're seeing in the literature that's out there and the marketing promotions that are out there are telling us these wonderful savings that we're getting in energy. And then when you look at the real meter readings, first of all, you find that only about, well, I'd say probably less than half the buildings that are being talked about right now have metered consumption. And those that have metered consumption, the difference between what was modeled and what's actually being used may vary by a factor of 2 or 3, where the almost invariably the estimated energy consumption is much lower than the actual. So we've got a lot.
Yeah,
I'm sorry.
I've heard that as well. We have in our normal time about 5 minutes left, so I'm hoping you could answer the question that's on the screen: who's accountable for assuring building performance?
Okay. Let's tackle that for just a minute. I had a chance to testify before OSHA many years ago in the 1990s. There was a bill being introduced at that time, and it gave me an opportunity to think about this in some detail. So the commitments needed for continuous accountability, I would propose, are 3. That we need to explicitly identify an accountable person, a pair of eyeballs, for each phase of the building's life: planning, design, construction, operations. That identification should be empowered with authority to assure building performance. Oftentimes what we find is that the person who's accountable or responsible for the performance of the building doesn't have control of the budget. So they can't do anything about it, and they're told that they have to reduce maintenance, or they have to defer maintenance or something else, and they're stuck. The third is that the accountable person should be educated and trained to assure adequate building performance. what we're finding many times, especially as we get into high-performance buildings, the training level of the skilled worker that's operating the building, and even the designers, doesn't match what's going on in design. One big example for me is controls. Very seldom do I find the architectural firm or the engineering firm actually writing the performance standards or the performance criteria for controls. It's almost always turned over to the controls contractor. And so accountability is abdicated in that particular situation. What I like to look at is what I call the wheel of accountability in terms of performance criteria. So when we get in the planning stage, this is where we set our criteria. The accountable person in this case would be the owner, who transfers the accountability to the planner. We get into design, and now we begin to translate the performance criteria. And now you've got the designer, the builder, and the owner who are accountable for the translation. Once we get to construction phase, we get the builder together with the designer, the owner, and the tenant who validates the compliance with the performance criteria. And then when we get into operations, we have the owner, the manager, the tenant, and the occupant who assure compliance with the performance criteria. So there's a whole wheel of accountability that we can transfer from one to the other if we would only do that. And I think with that, maybe we can talk about where to from here.
Thanks, Jim. A question has come in from Doug Langmead that I think relates to how the various costs compare to rental income. There are different values in different parts of the world. So you mentioned a manager might, cost to a building might be $400 a square foot. But if you've got a building that's all rental and you don't have personnel in it, so the formula would change a lot?
Oh, great question. There's a natural tension that exists between the building owner and the leaseor, or the leasee, I'm sorry, the person that is leasing space in that building. The leasee tends to want to maximize the occupancy density of the space. The building owner wants to optimize the occupancy density, wants to fill the whole building. But the tenant is only interested in one little part. So basically what happens from a tenant standpoint, the cost of salaries is going to be considerably higher than the cost of energy. It'll probably go up more than the number I just quoted.
Okay, and as a last question, this isn't something they taught me in architecture school. So for those on the call, and where do you go for this lifelong learning? Because this certainly makes a lot more sense to me than chasing recycled content in metals. You know, if we're really after building performance, where do design professionals go?
Well, you know, I'm bothered about that a lot. I'm not sure we're gonna change it immediately. I think what we're gonna have, we can find places, a few places that really have this approach. But to make a change, I think it's going to have to start almost at the grade school level and through high school. We're going to have a generational change to understand why we have the built environment. And it's not just for marketing. You know, there's real functions that go on, and there's real health and safety issues that have to be dealt with. One of the questions that I was trying to answer some time ago is, from a professional architect or engineer standpoint, who's licensed to protect from the state to protect the health and safety of the people within their discipline, or within their discipline to protect the health and safety. How many people have actually taken formal courses in health issues that have that legal responsibility? Well, it turns out progressive architecture many years ago did a survey on that, and I think the number, from what I find in seminars and everything, still holds. It's about 2% of the professional architects and engineers that have ever had any formal coursework in health sciences. We need to get this integration done. We're working on this low vision lighting problem right now. One of the most insightful things, no pun intended, but one of the most insightful things that we've had is ophthalmologists and optometrists working together with architects and engineers to come up with the criteria. It really makes a difference. And I think we've got to develop a demand for that within the society. It's not there. I'm looking at undergraduate courses in architecture and engineering. Unfortunately, it's not being trained. The apprenticeship programs, some of the apprenticeship programs are dealing with it. Others are not. I think we have to develop a skilled and educated and skilled workforce, together with skilled and educated designers and professionals.
And I think that's why case studies become so important, whether it's zero net energy buildings or how LED lights and more fixtures with task lighting can work all the whatever way each of us comes to this profession. But with that, we need to wrap up for today, and I'd really like to thank you very much. I felt that your presentation was brilliant and lets me know how much I don't know. So we need to find a way to continue this dialogue, and perhaps we can have you back in a future CSI webinar to narrow in on just one area that you've started to present. Did you have any last words for the group, or?
Well, it's been a pleasure. I think the comments that you've made make my day. I think we really need to see a paradigm shift in how we're dealing with the buildings, and just to get lead points is probably not the answer.
All right, thank you again, Jim, and thank you all. Once again, thank you to Jim Woods.
Well, thank you very much.
All right, have a good day, all.